All right, let's get started with note set number 1. Welcome to EEO301, Digital Signal Processing. My name is Professor Mark Fowler. So let's get into this here. We're going to be talking about this chapter 1. Oh, let me change my color here. There we go. I'm trying out a new program here on my iPad. So let me change the thickness here. That's a little bit better. Maybe I can erase here. Thanks for bearing with me here. Should have tried this out ahead of time, but I didn't. Next time I'll be much better. Try a little bit bigger. See how that works. There we go. Okay, so we're going to be covering Chapter 1 of Proachus and Monolachus, 4th edition. That's the textbook that we'll be using for this course. And is usually the case, Chapter 1 is just kind of a nice overview of the kinds of things that we'll be talking about and put everything into context. Set down some definitions, notations, and things like that. So here is a scenario that we're interested in talking about in signal processing. So we've got some sort of sensor that's picking up some sort of physical CT, continuous time signal. So our sensor might be a microphone or something like that, any kind of sensor that will convert a physical signal into some sort of electrical signal. And it's going to go through some analog electronics, which will be like transistors, op amps, resistors, capacitors, and inductors, and such. And we end up with some continuous time signal, which we'll call x of t. And the key thing is that that continuous time signal exists for all instants of time. So there's no point in time in which we can say there is no value. And then we put it through our A to D converter here, ADC. That's an analog to digital converter. And what that does is it takes samples of the signal. We're looking in this little yellow box here. Takes samples of the signal every so many seconds and puts those into a sequence. And you'll notice here that we are no longer indexing those by time. We're indexing them by an integer, n. So it's just a counting index. And you'll also notice that we think of the plot as those blue dots with stems. So it's a stem plot. And there is nothing in between them. On the plot, I show a red dashed curve to show where the continuous time signal exists. It's not really there at this point. That's just showing us what was there at the input to the A to D converter. So that is our discrete time signal, and we index it by an integer. If we know the rate at which we are taking these samples, or equivalently the spacing in time between the samples, then we can convert from the sample spacing to the actual time spacing. So that comes out of the A to D converter, and we then have a discrete time signal. And then here's the box that we're interested in describing, although we are going to talk about how the ADC works. But all the magic will happen inside this DSP, which is basically just some sort of computer or some digital processing, discrete time, digital circuit that takes these samples going in, processes them in some way, and creates a new stream of signals coming out. And so that's our input signal, and is x of n, and our output signal is y of n. And so then we end up with a discrete time output signal. And now that could also then be run through a digital to analog converter, or a DAC, to convert back. And actually I say, not shown here, and I'm lying. I am showing it here, so I didn't edit that out of my slide. I had originally intended not to show it, and then at the last minute I did show it. So that's not true. We convert it back to analog, and we get some output signal y of t. So we really can view this whole thing as some sort of continuous time system. We put in x of t and we get out y of t, or even going further back, we put in some signal not named on the chart into the sensor, and we think of some other signal coming out of the output of the DAC. So our job in this course is to understand mostly what goes on inside that DSP, and we'll also spend a little bit of time talking about the A to D converter as well as the D to A converter. So the things that we're going to be focusing on here are sampling theory. That will tell us a little bit about at least the theoretical aspects of how an A to D converter needs to work in order to properly take those samples fast enough so that our sampled signal is a viable representation of the original continuous time signal. And then we're going to talk a whole bunch about frequency domain models using the discrete time Fourier transform, as well as the discrete Fourier transform. There'll be a lot of FTs that we'll be talking about. We'll later in the course talk about the FFT, how to efficiently implement the DFT, and we'll also have the Z transform, which is a generalization of frequency domain concepts. And so we'll have these models for discrete time signals as well as discrete time systems. And so these things provide us with the way of understanding how a DSP system should work. And then we'll talk about some processing structures for implementing DSP systems and some methods for designing DSP systems. Primarily we'll be talking about discrete time filters, how to design and implement a low pass filter, a high pass filter, and so on. So that's kind of where we're going in the whole class. Section 1.2 of the textbook talks about classification of signals. I'm not going to go into detail, so I would encourage you to read that. But the things that we have highlighted here in bold and underlined, those are the flavors that we're going to be talking about in this course. So we'll be talking about a single channel signal that's discrete time, and it's continuous valued for the most part. So when we go through a true A to D converter, not only does it sample in time, but it also discretizes in value. So we might have an 8-bit A to D converter, so we can only represent 2 to the 8 different values, and so we have to decide how closely spaced those 2 to the 8th different values are and what range they will cover. So we will talk a little bit about discrete valued, but primarily when we talk about a discrete time signal, unless we say otherwise, for purpose of just making it easier to deal with, we will consider it to be continuous valued. Obviously, in the real world, all signals inside a computer are not only discrete time, but also discrete valued. But we're going to ignore that for most of the time. Then we've got random versus deterministic, and there are entire courses that focus just on the random part, and so in this course we'll focus entirely on the deterministic case. So I encourage you to read that section to get a little bit more insight. What I want to talk about here is some notation. Now this notation is a little different than what is in the book by Proakis and Manolakis. This is actually in a book. This notation is in a book by a guy named Peratt, last name Peratt. It's a really nice book, but it's quite a bit more theoretical than Proakis and Manolakis, so I didn't choose it for the course textbook because I wanted to stay at a little more practical level and Peratt is much more theoretical and really at a much more advanced level, more appropriate for like a first year grad level. But I like his notation. So we'll be talking about a lot of different transforms, Fourier transforms, Z transforms, and so forth. And you should have seen all of these. So if you're looking at this slide saying, I don't have a clue what any of these things are, then either you haven't had the Signals and Systems course that prepares you for this, or you had it and you've forgotten it, in which case you might want to go back and review. But part of what this slide is for is to help you refresh your memory. So we've got continuous time signals, and we've got the continuous time Fourier transform of that. So that's defined here by this integral. Previously you may have seen this defined in terms of, without this superscript. One of the nice things about this notation is that this superscript here, which I just erased, gives us a really nice way of indicating what this capital X function is really representing. So the superscript capital F will tell us that this is a continuous time Fourier transform. Now, something else that you might notice different from maybe the Signals and Systems course that you probably took with me is that we're using a capital F here. Now, that's actually Proakis and Monolakis' idea, not Peratt's. So Proakis and Monolakis use a capital F to represent the continuous time frequency. To be honest, I hate that symbol. I really don't like it. But I tried to stick with it. I may have drifted away from that at points in the course, but I did try to stick with it as best I could. Down here we see that we have the inverse Fourier transform that tells us if I'm given the CTFT of a signal, how to get the original signal back. So that's the Fourier transform for continuous time signals. And then we have something analogous to that, which is the Fourier transform for the discrete time signals. And that is called the discrete time Fourier transform, or DTFT. And that's why I tend to refer to this as the CTFT, to just draw a parallel between them. So the DTFT, you can see, is defined very similarly for as to the continuous time Fourier transform. And let me just try to get some of this stuff off from the slide here. Let me just try to erase some of it here. I guess I need to look into this to see if there's a command that will allow me to clear all ink off the slide. This is my first time using Explain Everything on my iPad to do a video recording. So I've used Camtasia Studio in the past on my laptop. But I was interested in trying this out. So I have a little bit of a learning curve here, and I should get on that. Anyway, we see the main distinction here is that because we have a continuum function, we can integrate. Over here we have just a sequence of numbers, so we can't integrate, but we can sum. But other than that, the structure looks exactly the same. And now we're going to use a lowercase superscript to help us remember that this is the discrete time Fourier transform. And you can see now why, hopefully, why this superscript is very nice, because we're going to, at certain points, be substituting in different changes of variables and so forth. So if we had, if we didn't have these superscripts here, so for the time being, let's just imagine that this capital F is gone and this lowercase f is gone. I have x as a function, capital X as a function, capital X as a function, and to tell them apart, I'm at the mercy of being able to identify them only on the fact that this one has a capital F and this one has a lowercase Greek omega. But as soon as I start substituting in different variable changes, as we will have to do, I lose track of what is what. And so this superscript idea, even though Proaicus and Monolacus don't use it, the superscript idea helps us see, oh, this is the DTFT and this is the CTFT. So they are two different things, and it helps us keep a different notation for them. Down here we have a way of inverting the DTFT to get back the original discrete time signal, and you can see the similarities between the inverse CTFT and the inverse DTFT. In this case, both are integrals, and that's because the DTFT, like the CTFT, is defined on a continuum, so we need an integral to process it. Other than that, everything else is pretty much the same, except we only have to integrate from minus pi to pi, whereas over here we integrate from minus infinity to infinity. And so the main reason that we only have to go from minus pi to pi, and we'll explore this in just a little while, I think maybe in the next set of notes we'll get a little bit more into this. But if you remember from your signals and systems class, that the DTFT is 2 pi periodic. So once you go outside the minus pi to pi, you're just getting replicas of the stuff that lies between minus pi to pi. So that's why we only need to look at it between that region. So other than that, everything else is okay, and I actually just noticed an error here. This should be a lowercase omega to match the thing that we have here. Hopefully you can change that in your notes. So that's the DTFT. And now we go to the Z transform, or the ZT, and that's something that we'll indicate with a lowercase z in the superscript position, because again, we can't rely on the argument of the function to tell us what it is, because there will be times when we will replace z by something entirely different, and we'll need to know, be able to keep track of the fact that, oh, when we use capital X here, it's a Z transform. When we use capital X someplace else, it's a DTFT or a CTFT. So these superscripts give us a way of keeping all of this straight. Now, a key thing to remember is that there is a link between the Z transform and the DTFT. So if we look at this summation here, and we just make this substitution, if we let z be replaced by e to the j omega, well, we have a z to the minus n, so z to the minus n becomes e to the minus j omega n, and that's actually what we have right there. So if we make that substitution, the z transform kind of collapses, almost literally collapses to the DTFT. And if you remember from my signals and systems class, that was the basis of the DTFT being embedded on the unit circle of the Z plane. So you might want to go back and refresh your memory on those things. And then finally we have the DFT, which in some sense is related to the DTFT. So if we look at this up here and we imagine that we have a signal that is only non-zero from n equal to 0 up to n equal to capital N minus 1. So for a finite duration signal, this summation looks just like this, just at specific values of omega. And so what specific values are they? Well, just comparing that, we've got the minus j and the n, so we've got a minus j and we've got a little n in there, and so what's left is 2 pi k divided by capital N. And so as we let k go over these values, we are getting just a certain set, a discrete set of frequencies, and so that's what the discrete Fourier transform is. And once we have it, which we're using a superscript lowercase d to indicate that, we can do a summation to get back our original signal. So a lot of stuff on this slide, but stuff that you've probably seen before, but just a few wrinkles here with just some new notation perhaps. Also, you should have seen this when you took my Signals and Systems class. This is just all the connections between the various ways of characterizing discrete time systems. So we've got over here the difference equation, and we've got, through the z transform, we can convert that into a transfer function. We can talk about the pole zero diagram, and well, before we get into that, you can see the structure here for the difference equation and how by inspection we can write down immediately what the transfer function looks like. Once we have the transfer function, notice that it's in terms of z inverse here. If we convert it into, get rid of all the z inverses by multiplying by an appropriate z to the power on the same power on the top and same power on the bottom, clear out all the negative exponents, then find the roots of the numerator and the denominator. We'll find the poles and zeros of that transfer function, and we can plot a pole zero diagram, which, if you remember, tells us an awful lot about how that system behaves. We can determine whether it's stable or unstable, whether it has some resonance or not, whether it's a low pass, high pass, all sorts of different things. From the transfer function, if we do an inverse z transform, we can get back to the impulse response. And the impulse response gives us something that we can convolve with the time domain input signal to get the output. The transfer function, h of z, we can multiply times x of z to get y of z, the output. We can also take the transfer function, evaluate it on the unit circle, and we get the frequency response. The frequency response would be a dTFT. We can take that dTFT, h superscript f of omega, multiply it by the dTFT of the input signal, and get the dTFT of the output signal. So hopefully these are ideas that you remember from Signals and Systems. And then one thing, we didn't really stress this too much in Signals and Systems, but we'll talk more about this in this course. From either the difference equation or the transfer function, we can get a block diagram that will really give us insight into kind of how to implement the system, either in hardware and or software. And I put that straddling this line between the time domain and the frequency or z domain because it can be interpreted in either way. And we'll see that later on as we get more into this. Okay, I want to spend a little bit of time, just real quick, refreshing your memory on sinusoidal time functions. So a sinusoid has three parameters that nails it down. We've got amplitude A, which sits out in front. We've got a frequency f0 in hertz, and you can see that once we multiply that by 2 pi, we are converting it into radians per second. So anything that shows up in front of the t inside of a sinusoid must be in radians per second. Excuse me. So the 2 pi f0 must be in radians per second, and from that we can work out that f0 itself must be in cycles per second. So then we can find out that we basically have radians per cycle times cycle per second times second is the what we're doing with those three. So we've got the 2 pi is in 2 pi radians per cycle, the f0 is in cycles per second, the t is in seconds. So if we look at all of those units, we end up getting that product gives us radians. The phase is in radians. So the whole argument of any sinusoid, whether it's a sine or a cosine, must be in radians. So the other thing that we see here is the relationship between the phase and the phase phi and a time offset. So if we were to look at this sinusoid on an oscilloscope, the axis that we're looking at it with respect to is a time axis. And so if we were to measure from some reference point to some other point and say that's a time, if we call this point time equal to 0, that t0 is going to be a time that can be linked back to phi. And so it's pretty easy to figure out how phi and t0 are linked together. Also, we have the period of the sine wave is related to the reciprocal of the frequency of that. So you should have seen all of this stuff before, and shouldn't be anything new. You should also know that a real sinusoid, the things that we have in the real world, can be broken down into a sum of two complex sinusoids, one rotating in a clockwise direction because it's a positive j times some exponential, and a negative j, since the rest of this is the 2 pi f0 is positive. This thing will be rotating in a counterclockwise. So this one goes, so this one goes counterclockwise. Let me just write this all down so that we get it nailed down here. The positive one goes counterclockwise, or anti-clockwise for any of you out there from England. And then the negative frequency one goes clockwise. So we can see those two here just as e to the j theta and e to the minus j theta. So that's the static version of Eulers' formula. And if we think about that rotating now, we think about this angle here changing, and so each of those things is going to be rotating at a rate of 2 pi f0 radians per second. And this should just help you remember and connect back to how Eulers' formula works. We've got this form of Eulers' formula, and then we've got this way. And this is just a handy way. In fact, all it really is just converting back and forth between rectangular and polar forms, basically. Okay, so we've got that nailed down. And then, so if we look at this a little bit farther, we, using Eulers' formula, can take this real valued sinusoid and we can split it into these two parts. And here we're showing the positive frequency part here rotating counterclockwise, and the negative frequency part rotating clockwise. And notice that at every instant of time, those two vectors will be perfectly balanced so that they end up canceling each other out on the imaginary axis. So whatever the imaginary part of these is, what happened? Oh yeah, I was erasing. Whatever the imaginary part is, it's wherever they are, that will end up canceling. Or alternatively, if you think about these two things adding, if you remember how to add vectors, you'll realize that this falls on the real axis. So at every instant of time, because of that the negative relationship between these the angles of these two components, the imaginary part always cancels and gives us back something that is real valued as is necessary. So I would encourage you to go to these web links. Hopefully they're still active. If they're not, please let me know. And you should be able to explore and see some illustrations of these kinds of ideas. So we talked about sampling briefly, and we alluded to the fact that we have to sample fast enough. And so later on we'll get into the theory of sampling. You should have seen that to some degree in your signals and systems course. But the question we need to answer is, for a given signal, how closely should the samples be spaced in time? Or to say that another way, how often should we take the samples? Or to say that in yet another way, what is the rate at which we should take the samples? How many samples per second? Like I said, we'll get into this in more detail, but basically we want to determine how fast do we need to sample this so that the stream of numbers that we get coming out of the A to D converter will appropriately represent the continuous time sinusoid going into it. So let's just take a look. Suppose we have these samples that are shown here, just a sequence of numbers, and your eye will automatically look at those and go, oh, I see the sinusoid. So your eye just automatically draws kind of the sinusoid through it that you would think, and we get something that looks like this. But if you look carefully, there's no reason why we can't have a much higher frequency sinusoid that's shown in the red curve here. And you can see that indeed the samples that we have fall on the red curve just as much as they fall on the blue curve. So those samples could have come from that higher frequency. So from the samples that we have up at the top, there's no way to know ahead of time which of these two sinusoids, and in fact there's infinitely many different sinusoids of higher and higher frequencies that just as legitimately satisfy these samples. How do we know which one was the one that we sampled? And basically we need to have an agreement that we have to agree ahead of time that if we took samples, we took them fast enough so that the actual signal gets represented so that it's obvious which one is right. So just by agreement, it would have been this one that we would have taken the samples on. We would be working in our system to make sure that we never get such a high frequency as the red one sampled at the rate which we're using here. So we'll talk more about that later. And this idea is called aliasing. We can see that the red sinusoid looks like or has the same appearance from the samples as the blue one, and so those two sinusoids from the point of view of the samples are kind of equivalent to each other, and so we call that high frequency aliases down into the lower frequency. We'll talk more about that later. So to just see kind of how this can physically happen, let's suppose that we're taking our samples every ts seconds, and so our sampling rate would be 1 over ts, and we'll call that also our sampling frequency, and the units of that will be samples per second. So if we start with this as our continuous time sinusoid, and we're taking samples every capital TS seconds, that just means that we're going to replace t, little t, gets replaced by an integer n times t sub s. And so if we replace t by this quantity, we end up with the nts right there. And so now if we look at this more carefully, we can group the other stuff and leave the n by itself, in which case we can define that new thing as some omega 0. And that will be some discrete time frequency. And we can see that this is the equivalency between the continuous time frequency omega 0 f0 and the discrete time frequency omega 0, and we see that they are linked by the sampling frequency f sub s. And where did that f sub s come from? Well, we just used this relationship here to replace the fs. So we can think about, once we have this omega 0, which is in radians per sample, we can think about each one of these terms that makes up this cosine as a complex vector on our real imaginary axes, on our complex plane, and it's rotating at a rate of, kind of a stepped rate of omega 0 per radians per sample. So if we do an example where omega 0 is pi over 8, this thing, every time we increment n, it jumps along these points. So one of these is rotating counterclockwise and the other one is rotating clockwise. And so at each n, this thing just jumps pi over 8 for that particular example. Now, I'd also like to point out that unlike in my signals and system notes where I used capital omega for the discrete time frequency, here for the Proakis and Manolakis book, they use lowercase omega for the discrete time frequency. So a few things to just keep track of there. Now, this is just illustrating how we can end up with two sinusoids looking the same. So this is just another way of illustrating what we saw previously, where we had the blue curve and the red curve, both sinusoids and both going through the same set of samples. So this is just another way of visualizing it. So the top four plots are positions of the two complex sinusoidal components for the case where the frequency is 7 pi over 8. So that is a frequency that is less than pi. And then we have 9 pi over 8, which is a frequency that's greater than pi radians per sample. And we'll see that for these two specific choices, we can't tell which of those two we're actually operating at. And this is another reason why we only need to look at a discrete time Fourier transform between minus pi and pi. So at n equal to 0, both of these scenarios start with both red and blue vectors at that position. Then we go to a situation where n jumps to 1, and what happens? Well, on the top, things bump ahead by 7 pi over 8. So this jumps over here to this position. And then the other one that moves in the opposite direction moves negative 7 pi eighths over to that position. Now, what about the one that has a frequency of 9 pi over 8? Well, the red one that started here now goes all the way past pi and over to 9 pi over 8. And the blue one that started here now goes more than pi over to there. But notice that the two positions are exactly the same as what we had up here. It's just that the red and the blue are swapped with respect to each other. But that doesn't matter because all we're really looking at is the sum of these things. So it doesn't matter at all that they're, that the position of blue and red individually are different. What matters is just that they have the same sum. Then at n equal to 2, this red one is going to move ahead. The red one's going to move from here ahead to there. And the blue one's going to move from here ahead to there. And likewise, I'll let you suss it out, but the blue one will move all the way around it'll move from here all the way over to there, and vice versa. The red one will move from here all the way around to there. And so again, we see that we end up with exactly the same combination of vectors adding together to give us something that's real valued, and so on and so on and so on. At every value of n, we get the same sum of two vectors. So the resulting real valued sinusoid is the same for each of these cases. So it's impossible to tell apart a discrete time sinusoid with a frequency of 7 pi over 8 from a discrete time sinusoid with a frequency of 9 pi over 8. And there are other combinations that are also indistinguishable. And I encourage you to try to play around and find other ones for which that will be the case. Okay, one more slide and then we'll finish up. So to avoid this thing of aliasing, where a higher frequency looks like it could have come from a lower frequency, we will just have an agreement that unless told otherwise, we should assume that the frequency that we're trying to interpret should lie between the range of, whoops, what happened there? Yeah, okay, getting used to the program here. Should lie between minus fs over 2 and plus fs over 2, where fs is the sampling rate that we are talking about. So the continuous time sinusoid must have a frequency that is less than fs over 2, and that is basically the idea of sampling, that we need to sample twice times the highest, at a rate at least twice times the highest frequency in the signal. And so if you're familiar with audio, digital audio, you're familiar with the idea that humans can hear up to 20 kilohertz, so continuous time audio signals are limited to no more than 20 kilohertz. And if we sample at more than twice that, we should be fine. Here's a typo. That little k there should be just a 1. So if the standard CD sampling rate is 44.1 kilohertz. So I missed the 0.1, substituted in the k. So this quantity here should be 44.1 kilohertz. So please make that correction in your notes. Okay, so a lot of review of stuff that you've seen before here, and also setting the stage for things to come. We will revisit and use a lot of these ideas all throughout the course. So if you're unsure of some of these ideas, make sure you kind of revisit and review some of these concepts before we get too far into the course. And you find yourself unsure how to proceed. Okay, so we'll stop there, and I'll see you in the next slide, next set of slides.